In the previous class, we were discussing mean value property for the solution of heat equation. Let me again state that, and we almost completed the proof. So here is the statement of this mean value theorem. So if U is solution of the heat equation in a region in Rn cross R, then for all xt in Q, uxt is equal to this double integral. In fact, it's n plus 1 dimensional integral, and we discussed why it is called a mean value property because of this region. This integral is equal to 1, so this weight is 1, so this uxt is the mean value of uys over this extr, that is heat ball, with this weight. Okay, so I almost completed the proof, just one last line, and the proof started with some reductions. So we can assume that x equal to 0 in Rn and t is equal to 0 in R, and that is just by translation, and this integral does not change. So we have to prove that u00 is equal to this integral. Okay, so for that we just forget this factor 4, consider this function chi of r defined by this integral, and we showed that chi is a constant function of r. Okay, so that involved some computation, and only in the last part of the proof we use that u satisfies the heat equation. So this del u by del s is replaced by Laplacian u, and proof mainly relied on divergence theorem. Okay, and this important function coming from the nature of the set E a heat ball extr. Okay, so once we know that chi is a constant function, so this chi of r is equal to limit chi rho 0 tends to 0, but then we can write this chi rho by 4 is equal to 1 by 4 to the n, this integral over e rho, and then you add and subtract this u00, and because of that integral is 1, so this is just 1. Okay, and by continuity of u, the first integral goes to 0 as rho tends to 0, so we are just left with u00, and that's what we wanted to prove. Okay, so again let me just recall this heat ball. Ext r, so x is in Rn, t is a real number, and r is a positive real number. Okay, so if okay, what is extr? So let me just again recall that. So this is set of all ys in Rn cross Rn R such that s is less than or equal to t, and this is the heat kernel. So xt ys bigger than or equal to 1 by r to the power n. So if y s belongs to extr, so using the expression for the heat kernel, we saw that this is equivalent to, so s lies in the closed interval t minus r square by 4 pi t, and then y lies in the bond uh, and x minus y square. So y lies in the ball with center x, and radius square is given by this number log uh, 4 by r. You can check that. So that's not divided. This is, or some n is missing, so let me uh, some n is missing. Okay, so it is here only. Let me just go there and instead of rewriting it, uh, it is here. Okay, so this is for 0, otherwise you will get x minus y square, and so here I have taken this x equal to 0 and t equal to 0, but that just translates, so that's uh, let me write. Okay. Okay, so this is n log r plus minus, let me write it here, n by 2 log 4 by t minus s. Okay. So using this domains for s and y, so it then easy to, so not difficult to evaluate. this integral 1 by 4 to the 4 into r to the n, and this n plus 1 dimensional integral mod y square s square dy by ds. So since the integrand is non-negative, we can integrate as an iterated integral. So first one integrates with respect to y using this bound, and then you integrate with respect to s. And even integration with respect to y, so since this is a radial function, so we can use spherical coordinates. So with this, we move to another interesting property of the solution of the heat equation, and this is referred to as backward uniqueness theorem. So let me first state the theorem, and then I will remark on its interesting properties. So again, let omega be a bounded open set in Rn with smooth boundary, del omega, and T is any positive number, and consider this cylinder. Okay. So this smooth boundary is required just because we want to integrate by parts, and the divergence theorem should be valid. Only for that reason we are assuming that smooth boundary. Let U1 and U2 be solutions of the following heat equations. So del T Uy equal to Laplacian Uy in omega t, and Uy is equal to G on del omega cross 0 t. So this is a Dirichlet problem, Dirichlet boundary value problem. Okay, so the important thing here is both U1 and U2 satisfy the same boundary condition G. So G is not changed. Okay. Then the statement of the theorem is if U1 xt is equal to U2 xt for all x in omega, then U1 is identically equal to U2 in omega t. So that's why it's called uniqueness theorem. It's backward because at a positive time the condition is given, so namely that U1 and U2 are equal, and the conclusion is that U1 and U2 remain same for all t less than t. Okay. So the importance of this theorem is that no assumptions on the initial conditions on U1 and U2 are made in the statement of the theorem. So there is no statement regarding the initial conditions on U1 and U2. And we have already seen for the initial value problem, to obtain a uniqueness result, we have to make some growth assumptions on the solution. Okay, and in this theorem, no such assumption on the growth of U1 and U2 is made. And yet, this uniqueness statement is made in the result. So that's why it's interesting and also important. You know, with also minimal data, we are claiming the uniqueness of the problem. Okay. So the proof uses energy method. Okay, and this energy method we also use it in wave equations. Okay, and this heat equation also enjoys some energies. Okay, energy estimate we can derive on them. Okay, so first some again reduction. Since the problem is linear, so linear equation and linear boundary condition. So put u equal to u1 minus u2, then you satisfy the heat equation in omega T, and since G is same, so U equal to 0 on the boundary, del omega cross 0. This is the boundary of the cylinder. Okay, and here comes the energy. Okay, so E is the energy. So put E of T equal to integral omega U square xt dx. Okay, so you integrate only with respect to x. So this is a function of T alone. Okay, so and this represents uh, the total amount of heat at time t, that is in the domain omega. Okay, and now we are given that E of t 0. Okay, if you see the hypothesis, u1 of xt equal to u2 of xt, that big T. So u equal to 0 at t equal to capital T. Okay, that's given to us, and we need to prove that Et is less than Et equal to 0 for all t less than big T, because then this integral is positive. So if we prove that this is 0, then this is 0 everywhere. Okay, and now we proceed to do that. Okay, and now we use this energy, and so that is a function of t alone. So you differentiate with respect to t. So just see how the energy varies with t. Okay, and this simple, very simple thing. So this you get 2u ut, and you satisfy the heat equation. So ut is replaced by Laplacian u, and then you integrate by parts. Okay, so you get minus 2 integral omega grad u square dx, and there are no boundary condition as u equal to 0 on the boundary of the cylinder. Okay, there are no boundary conditions. So we'll differentiate one more time. So second derivative of E with respect to t, d square E by dt square, and again you use the last expression, so you get another 2 there, so minus 4 grad u dot grad ut. Okay, and again integrate by parts. Okay, that's, so you get ut grad u, Laplacian, and again there are no boundary condition as u is 0. And now again you replace ut by Laplacian u, because you satisfy the heat equation. Okay, so we'll get finally 4 times integral Laplacian u whole square dx. Okay, and now we compare this the first derivative of the energy with the second derivative. So some simple estimate. So d by dt is, I am just using this expression, d by dt equal to 2 integral u Laplacian u, and when I take square on both sides, so I get 4 this integral whole square, and here I use Cauchy-Schwarz-Bunyakovsky inequality, and this integral is less than or equal to integral u square dx to the half, but there is a 2 there, so that it becomes 1, and similarly that one. Okay, and now this first integral is nothing but the energy integral. Okay, so Et is just integral u square dx. Okay, so if I take this 4 inside here, then that is precisely d square E by dt square. Okay, so we have this d by dt whole square is less than or equal to Et into d square E by dt square. And now to complete the proof, we assume on the contrary that E of t is positive for E is always non-negative, so E is positive for some t less than t. So we'll get a contradiction with that assumption. And then by continuity, so we try to find the first t less than t with this property, okay, and that just by continuity there exists a subinterval t1 t2 in 0t. So t2 could be big T such that et is positive for all t in this semi-open interval t1 to t2 and e to t is 0. So this t2 can be t itself, that is given to us. So okay, e of capital T is 0. Okay, so certainly there is one such thing. And now since et is positive in this interval, we can take logarithm. Okay, so for t in this semi-open interval, put f of t equal to log of et, and now we want to convert this second derivative of f with second derivative of et, and that simple calculation yields us d square f by dt square is equal to, so there is numerator and denominator. Denominator is et square and numerator is et into d square e by dt square minus de by dt whole square, and that is non-negative by the estimate we obtained for uh, de by dt square. Okay, so f capital F is a function of one variable such that its second derivative is non-negative in this interval, and that is equivalent to f being a convex function. Okay, so then this, because of this condition on the second derivative, f is a convex function. And by the definition of the convex function, we have that for any t in this semi-open interval and any alpha between 0 and 1, we have f of alpha t1 plus 1 minus alpha t less than or equal to alpha f t1 plus 1 minus alpha f of t. And if we translate again back to the energy function E of t, so we have to take exponentials. So we take the exponential both sides, and that yields this inequality for the energy. So E of alpha t1 plus 1 minus alpha t is less than or equal to E of t1 to the alpha, E of t to the 1 minus alpha. Okay, and this is true for all t in this semi-open interval. Okay, and now on the right hand side, you just let t to t2. Okay, let t goes to t2, and right hand side gives us 0. Okay, and that means we have that E of t is equal to 0 for all t in this t1 t2 in that semi-open interval, and that is a contradiction to our assumption. We have assumed that et is strictly positive in this semi-open interval, and that contradiction uh, completes the proof. Okay, so these are the some interesting qualitative uh, properties of uh, the heat equation. Uh, that's fine. And next we discuss one example again regarding heat equation. So this example. So let me state the uh, problem, and we will discuss the details perhaps in the next class. Okay, so this is a mixed problem. Okay, so this is the physical situation. So we have a circular cylinder in 3 dimension. That's 3D circular cylinder. So x square plus y square is less than or equal to a square, and z is in R. Okay, so ideal situation. So this is, if this is the z direction, so this is z direction. So we have this. So infinite cylinder. Okay, so this is, you can call it our omega. And initially, so at t equal to 0, so this metallic cylinder is heated, okay, so you assume that u equal to u1, okay, and the boundary and the boundary is maintained at u equal to u0. Uh, so here I should clarify this one, this initial condition. So let me just say what that is, okay. And then the problem is to analyze what happens for t positive. Okay, so initial condition, so this is just u x y z at t equal to 0 is u1 for x square plus y square less than or equal to a square, and z in R. Okay. u1 is just a constant. Okay. So we see that the initial condition, and again, okay, what is the boundary condition? So let boundary condition u of x y z t is equal to u0 for all x y such that x square plus y square is equal to a square, and again z in R, and T positive. Okay. So we see that this both initial and boundary conditions do not vary with z variable. Thus, the problem reduces to two-dimensional heat equation. So du by dt is equal to del square u by del x square plus del square u by del y square. So here again I am assuming the diffusivity coefficient is 1, so one can put a number depending on the that physical material. Okay, so for simplicity again I am taking this diffusivity constant 1. Okay, so we'll continue the analysis of this initial boundary value problem in the next class. Thank you.